Hi, myself E. Navin, rule number 49, and my topic is about minimum spanning tree. Spanning trees. Given connected graph G, V is known as a spanning tree of T V dash, E dash. It is a subgraph of G, that is V dash gives V or E dash gives E. Spans the graph V dash is equals to V. Forms a tree, no cycle. So E dash has mod V minus 1 edges. Minimum spanning trees. Edges are weighted. Find minimum cost spanning tree applications. Find cheapest way to write your house. Find minimum cost to send a message on the internet. Strategy for minimum spanning tree. For any spanning tree T, inserting an edge E new not in T creates a cycle, but removing any edge E old from the cycle gives back a spanning tree. If E new has a lower cost than E old, we have progressed. Strategy. Strategy for construction. Add an edge of minimum cost that does not create a cycle. Greedy algorithm. Repeat V minus 1 times. Correct, since if we would replace an edge with one of lower cost, the algorithm would have picked it up. Two algorithms. One is Prim's algorithm and another is Kruskal's algorithm. First we see Prim's. Build T incrementally. Pick lower cost edge connected to known incomplete spanning tree that does not create a cycle and expand to include it in the tree. And Kruskal's algorithm. Build forest that will finish as a tree. Pick lowest cost edge not yet in a tree that does not create a cycle. Then expand the set of included edges to include it. It will be somewhere in the forest. Prim's algorithm example. Starting from empty T, choose a vertex at random and initialize V is equals to 1 is equals to new. And from the starting vertex, then check for the minimum weightage which is adjacent to the starting vertex and mark it as read and do not visit it again. From that we should check whether the number of vertex is the number of edges is equals to number of vertices minus 1. This is known as Prim's algorithm. Prim's algorithm implementation. Assume adjacency list representation. Initialize connection cost of each node to find INF and unmark them. Choose one node, say V, and set cost V is equals to 0 and pre is equals to 0. While they are unmarked nodes, select the unmarked node U with minimum cost. Mark it for each unmarked node W adjacent to U. If cost U, W less than cost W, then cost W is equals to cost U, W. U W is equals to U. Kruskal's algorithm. Select edges in order of increasing cost. Accept an edge to expand tree or forest only if it does not cause a cycle. Implementation using adjacency list, priority queues and disjoint sets. Kruskal's algorithm. Initialize a forest of trees, each tree being a single node. Build a priority queue of edges with priority being lowest cost. Repeat until V-1 edges have been accepted. Delete minimum edge from priority queue. If it forms a cycle, then discard it, else accept the edge. It will join two existing trees, yielding a larger tree and reducing the forest by one tree. The accepted edges from the minimum spanning tree detecting cycles. If the edge to be added u comma v in such that vertices u and v belong to the same tree, then by, then by adding u comma v you would form a cycle. Therefore, to check find u and find v, if they are the same discard u comma v. If they are different, union find u comma find v. Properties of trees in Kruskal's algorithm. Vertices in different trees are disjoint. True at initialization and union won't modify the fact for remaining trees. Trees form equivalent classes under the relation is connected to u connected to u reflexivity, u connected to v implies v connected to u symmetry, u connected to v and v connected to w implies a path from u to w, so u connected to w transitivity. Time complexity summary. Recall that m is equals to mod e is equals to big O of v square is equals to big O of n square. Prim's runs is big O of n plus m of log n. Kruskal's runs is big O of m into log m is equals to big O of m log n. In practice, Kruskal has a tendency to run fast since graphs might not too dense and not all edges need to be looked at in the delete minimum operations. That's all about my topic. Thank you.